Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching KCET 60 out of 60 in physics series where we are discussing every chapters. We have started with second PU chapters and we are almost at the end phase of second PU. After that only two chapters will be remaining. Today we are continuing with the chapter atoms part 1, and if you follow our lectures then you should be definitely very close on getting that 60 marks that you are dreaming of in your KCET exam, right? So don't miss this video. We are going to discuss Rutherford's experiment and atomic spectra today, and if you want to download the class notes, also if you want to participate in KPL, that is KCET Premier League, happening every Sunday, free of cost, then don't forget to join our WhatsApp channel. The link is given in the description below. And without delaying any further, let's start with the chapter. First, let us look into the list of the content as usual. So what we are going to study today, we are beginning of atomic physics. So how atomic physics started? Atomic physics is a branch of physics. Okay, nowadays it is in terms of research, in terms of advancement, it is very important branch of physics, and how it all started. We will learn briefly about that. Then we will move to Rutherford's experiment, the famous Rutherford's alpha ray scattering experiment, also called Rutherford-Geiger-Marsden experiment. Okay, because there are three people involved in that experiment. Now next we will study about alpha particle trajectory, what is happening to the alpha particle. Then we will discuss about electron orbit, and then we will discuss atomic spectra to conclude part 1. In part 2 we are going to discuss about Bohr's model. Okay. Now let's start with the beginning of atomic physics. This is a very important little tidbit. Okay, J.J. Thomson discovered electron in 1987. So almost 120 years back, J.J. Thomson discovered electron. Okay, and from there onwards the beginning of atomic physics started. Okay, so what he said that the atom is constructed like there is a palm pudding model. This is called palm pudding model. It is nothing but your pudding cake, where you take a cake and on top of the cake you scatter the raisins, right? So if you have celebrated Christmas, you know during Christmas this kind of cake is very popular, where you are served with the cake with some cherries on top or some raisins scattered around. So he said atom is basically solid, because concept of atom was there. Okay, concept of atom was there in Indian philosophy, it was there in Western philosophy as well. Okay, even if you remember, Dalton gave the first atomic theory. Okay, so he according to him atom is the solid particle. Okay, according to J.J. Thomson, he said atom is solid, and since atom is electrically neutral, so whatever the electrons are there, so electrons are obviously loose, so you can detect it. So you can detect electron means this is negative. Okay, we know that electrons are negatively charged, so the overall base of the atom should be positive in nature. That's what he said. So on a positive base, electrons are embedded. Okay, so this was the first model. Next, according to this model, the positive charge of the atom is uniformly distributed, as I said, throughout the volume of the atom, and the negatively charged electrons are embedded in it like seeds in a watermelon. So if you eat watermelon, if you cut the watermelon, you will see that seeds of the watermelon are embedded inside throughout the watermelon. So the red portion of the watermelon is the positively charged atom and seeds are electrons. That's what he said. Now condensed matter, that is solid, liquids and gases, dense gases, all temperatures emit continuous distribution of electromagnetic radiation, that is right. Okay, so when you heat up solids or gases or liquids, and if you observe them closely, then you see that they all have a characteristic light, okay, coming from this. So using that light you can determine, okay, if this light is like this, then it must be hydrogen. If this light is like that, then it must be some other metal or other atom. So you can determine the type of the atom from observing the characteristics of that atom, but this model was not able to explain that, right? So what we have to do, we have to study the atom further and we have to discover the correct model for atom. Okay, so here this early 19th century, it was established that each element is associated with a characteristic spectrum radiation. As I said, each material has a characteristic spectrum. Using the spectrum, you can identify what type of material it is. So this model, palm pudding model, should if this model is correct, then each and every element, each and every atom should be same, and they should not have any characteristic radiation. But since we are observing characteristic radiation, that means this model cannot be correct. Okay, so this palm pudding model was failed to explain these 2 points. So Rutherford started an experiment. Okay, it's called Rutherford Geiger-Muskin experiment. Also it is called Rutherford alpha particle scattering experiment. So what is alpha particle? Let us, before going into the experiment, let us briefly understand what is alpha particle. Okay, alpha particle symbol is He42. Okay, He is helium. Okay, so basically it is a helium symbol, it is plus plus. Okay, He24 plus plus, this is the symbol of helium. I will explain this kind of symbol. I hope you have studied this kind of symbols in chemistry, but we will explain this kind of symbol in our next chapter, in nucleus chapter. There we will be explaining this, what is the meaning of 4, what is the meaning of 2. But for now you should remember this is basically a helium nucleus. Okay, even though we have not discussed about the concept of nucleus yet, but you can understand this alpha particle is nothing but helium nucleus. It has plus 2 charge, plus 2e charge. Okay, so it has a charge of equal to opposite that of electron, that is plus, and 2 electrons. Okay, so it has plus 2 charge. So you can consider this to be 2 times 1.6 times 10 to the power of minus 19 coulomb. So one alpha particle has this much amount of charge, and its mass is 4 times that of the proton. Okay, its mass is 4 times that of the proton. This is very handy. Sometimes they will ask you some questions related to alpha particle, even though not much is there about alpha particle anymore, but still if they ask you something related to alpha particle, if you know what is its mass, what is its charge, you might be able to solve that problem easily without any difficulty, because alpha particle is not properly in the syllabus. But since it is not there directly in the syllabus, if some question comes, that basically requires only this knowledge. So that's why I am giving you this information in this part. Now next, now let us talk about Rutherford's experiment. Okay, so what was the experiment? So he did one sample of beryllium. Okay, that is a source of alpha particles. Okay, and then he take a gold foil, we will discuss in a while, and then he sent these alpha particles along this opening, and then he observed whatever is happening around this. This is a detector. Okay, microscope is fixed in this, so using this arrangement he can detect. This is the gold foil. Okay, even though it is blue, this is the gold foil. You might be thinking, what is gold foil? This is the gold foil. Okay, this one is the gold foil, not this one. This one is the some screen. Okay, this is the screen in where you can observe what is happening in that experiment. So let us look into that. So 5.5 mega electron volt alpha particles emitted from bismuth 83214. Okay, not beryllium, bismuth. Okay, so the bismuth is used for as a source of alpha particles. So bismuth in normal room temperature, normal condition, they emit a lot of alpha particles, and this is used as the source of alpha particle, and the energy of the alpha particle is 5.5 mega electron volt. Okay, and the thickness of the gold foil is 2.7 times 10 to the power of minus 7 meter. So you can see that the thickness of the gold foil is very, very thin, and one of the reason that why gold was used, that gold can be made very, very thin. Okay, if you have eat sweet, okay, there they have said gold plating. Okay, gold plated sweet, silver plated sweet, that is actually in many cases actually real gold is used, and that is very, very costly, and real gold can be made very, very thin. Okay, even if you collect that gold and melt it, you will not get much gold. Okay, so maybe you will get 1 milligram or 1 microgram of gold. That will not help you in any way, so don't try that. Okay, but gold is very precious metal, and it can be made very, very thin. That is the one of the reason that gold was chosen for this experiment. In fact, you can consider this one foil, okay, one foil. Foil means thin sheet, okay. This one foil is considered to be having only one atomic layer, okay. So normally when we are saying a thick sheet, okay, it has multiple layers of atoms in it, but in case of gold you can consider to be one atomic layer of gold. So each point has one atom of gold, okay. So like that, since the gold can be made very thin, that's why gold is used, okay. The scattered alpha particle were observed. So once this alpha particle hit this gold foil, okay, once this alpha particles hit this gold foil, the electrons which are the alpha particles which are coming out of this gold foil are called scattered alpha particles, okay. So these are all the scattered alpha particles. These all alpha particles are coming out of the gold foil. So they are consisting of zinc sulfide. So this screen contains zinc sulfide, a screen and a microscope. So a microscope was used as well as a zinc sulfide screen was used, so that you can determine where all the alpha particles are going, okay. The scattered alpha particles on striking the screen produces a brief light of flashes or scintillations. These flashes may be viewed through a microscope as well, okay. So when these alpha particles are hitting the screens, they are creating small sparks basically, okay, small sparks. That spark can be visible, can be observed via microscope. That is the simple process of this experiment, okay. Now, what are all the observations? First of all, what are we expecting from this experiment? Let us get the goal straight. If palm pudding model is correct, then what can we expect from this experiment? So palm pudding model is saying that the atom is a solid thing, okay, if and electrons are scattered around it, okay. So it is a solid thing, that means it is a solid wall. You can consider this experiment was like a solid wall, and you have balls, okay, plastic balls or tennis balls, and you are throwing tennis balls towards the wall. Then what are you expecting from that experiment? So this is a wall, this is solid, right? Atoms are solid, okay. There may be in between two atoms, there may be some spaces available. So even though it's a brick wall, there are some holes in that brick wall. So maybe if you throw 10 balls, okay, you can expect 9 balls to come back and 1 ball to go through that gap, okay, 1 balls to go through that gap. So that was the actual expectation from this experiment if palm pudding model is correct, okay. But unfortunately you did not get that back. What we observed? We observed that there is a typical graph of total number of alpha particles that is coming out and for different angles. So what all we are observing? So we are seeing that if you throw a high number of alpha particles, about 10 to the power of 7 alpha particles, they are having very less an angle of scattering. What is the meaning of that? So angle of scattering means, if you go back to the previous part, angle of scattering means if you are considering this is the straight path, then this is the angle, okay, this is the angle of scattering, okay. And from this graph you can see that almost 10 to the power of 7, if you throw around say 10 to the power of 8 alpha particles, out of that 90% of the alpha particles are going with zero deflection. So they are not at all deflecting. So what is the meaning of that? You have a wall and you have a ball and you are throwing the ball. Instead of coming back, the ball is passing through the wall. So what is this? That means there is no wall. Wall is actually imaginary, okay, there is nothing there, and most of the space of the atom is empty, right? So most space of the atom is empty. So palm pudding model is washed away in that single experiment, okay. Palm pudding model was no longer valid, so we have to come up with a new model of atom. Why it is important? But because every thing in our universe is consisting of atoms, so we are consisting of atoms, our environment is consisting of atoms, so we want to study how they are behaving, what kind of behavior they will do, Okay, so starting from chemical reactions, starting from engineering, everywhere, this is very, very important. This is the starting point, stepping stone of most important branch of physics, that is atomic physics. So here we have learned that most part of the atom is empty, because if you see the graph, most atoms are getting undeflected, without getting deflected, and even if they are deflecting, it is less than 20 degrees. Okay, the deflection is very, very small, right? The dots in this figure represents the data points, and solid curve is the theoretical prediction based on the assumption that the target atom has a small, dense, positively charged center. So if you are getting this kind of graph, okay, these are the data points. These dots are actually observed during the experimentation. Okay, and this solid line was drawn based on the fact, if instead of having a solid positive base, if there is only a small tiny positive center, if there is a small tiny positive center, then you are getting you are expected to observe this kind of graph. And in fact, if you see the actual number that we are going to expected is that most electrons should have most alpha particles should have come back directly. That is, we are expecting this number to be high, but instead we are getting this number to be very, very, very low, right? So what we are expecting is that this number should be very low and this number should be very high. What our expectation was, the graph should have been like this if it was a palm pudding model. If it was a palm pudding model, we are expecting this kind of graph. Okay, so the number of particles that is directly getting reflected was very high, but instead of that, what we got was completely shocking, completely surprising, that we got whatever we are expecting so high, that is coming out to be very small. And if you plot this graph actually is very close to of a small, dense, positively charged center. So instead of having a full fledged atom with positively charged base, it is now considered to be a very small center. Okay, what is the name of the center? You guessed it correctly, that is called nucleus. Many of the alpha particles pass through the foil, right? So I explained it, many of the alpha particles pass through the foil. It means that they do not suffer any collisions. If there is a object here and you are throwing one ball, if it is collide, then only it will change the direction. But if there are, suppose say, one ball here, one ball here, and you are throwing, then there is a chance of collision is very, very low, right? Only if the ball is moving in this direction, then only it will collide and it will change its direction, right? But if the path is clear, coast is clear, I can go straight without any deflection. But sometimes I will deviate and I will collide. There will be some interaction between these electrons and this positively charged helium nucleus, and because of that we can say, okay, there are some interaction happening, right? But actually what we say, 90%, over 90% of the alpha particles, they do not interact directly, they pass through it clearly. Okay, so they do not suffer any collision. Only about 0.14% of the incident alpha particles scattered by more than 1 degree. So in fact it is not even 90%, it is 99.9%. Okay, 99.9% of the atoms, they don't scatter. Only 0.14% of the atoms, they scatter more than 1 degree. Okay, so 1 degree till 180 degree, only 0.14%. About 1 in 8,000, this is very important number, deflected by more than 90 degree. Okay, 1 in 8,000 deflects more than 90 degree. 90 degree means it is like this. This is 90 degree. Okay, so about 1 in 8,000. Rutherford argued that to deflect the alpha particle backwards, it must experience a large repulsive force. Okay, so if this electron is experiencing deflection more than 90 degrees, that means this is 90 degree, right? This is, suppose this is hitting like this and somehow it is going this direction, that means this is 90 degrees. But if it is coming back like this, then that means there is a something strong which is repelling this alpha particle. Alpha particle is positively charged. We know that alpha particle is positively charged, and there is something which is strongly repelling it. So strongly repelling means it is going towards this and then suddenly it comes back. Okay, so strong repulsion is happening, but the area of that thing is very, very, very small. Okay, so it must experience a large repulsive force. Okay, now let us look into one question from your previous KCET question paper. Is that a beam of fast moving alpha particles were directed towards a thin film of gold. That is the alpha particle scattering experiment. Instead of mentioning the experiment name, they have given you the experiment itself. Okay, three parts A, B and C of the transmitted and reflected beams corresponding to the incident part of it is A dash, B dash and C dash of the transmitted and reflected beams corresponding to the incident parts A, B and C. So A, B and C are incident. A is incident, B is incident and C is incident. They are all going in, whereas A dash, B dash, C dash are either transmitted or reflected or deviated. Okay, so this is the experiment. Okay, shown in the adjoining diagram. The number of alpha particles in A dash will be minimum. So they are sending alpha particles. Now which one will be minimum? First let us first understand which one will be minimum, which one will be maximum. So as we have seen that 99% of the incident alpha particle should pass, right? So 99% of the alpha particle should pass. So that is about 99% will pass. Okay, but about 0.14% will deviate like this. So this is the second one. And about 1 in 8,000 will deviate more than 90 degrees. So it is 1 by 8,000, which is a very, very, very small number, right? So now let us check the options. A dash will be minimum, wrong. A dash is maximum. So we will see where they have mentioned A dash is maximum. So in the option D, they have mentioned A dash will be maximum and B dash will be minimum. So what is B dash? Yes, B dash is the second one, which should be the minimum one, right? So from the given option, we can easily write that A dash will be maximum and B dash will be minimum. So you just need to analyze this diagram and answer the question accordingly. Okay, now this question when came in here, they have all four options wrong. I have personally corrected that question so that you have a correct answer, correct option to answer from. But if the question comes in your future years, they will definitely correct the options. So in some cases, if you find some questions, some options which are not correct, don't worry, you can answer them. Okay, because there is no negative marking. If you think the options, all options are incorrect, then you can answer it whatever you think is the closest answer, and based on that you will be scored. Okay, so here in this case, A dash will be maximum and B dash will be minimum, right? Now let's go back to our discussion. The repulsive force could be provided, the repulsive force that B dash in the diagram, you remember there is an atom and it is hitting back, right? So this is very small. This is very number of this is very small, but since we are observing this, there should be something which is repelling it. Okay, if everything was about to pass, then we could have said atom is mostly empty, right? Atom is empty, but atom is empty. Okay, but why some of the beams are coming back directly? There will be some explanation for that as well. So he said that a greater part of the mass of the atom, okay, the repulsive force could be provided if the greater part, so most mass of the atom, okay, is positive charge where concentrated tightly at its center. So at the center of the atom, all the mass and all the positive charges together sitting at the center. Okay, and most commonly the example that we give is our solar system. If you see our solar system, the most mass, most heavy object, that is the sun, is situated at the center of our solar system, and everything around it is rotating around it. Okay, even though it is not highly accurate description of the atomic system, but it is a very good approximation. Okay, this is a very good approximation, very good analogical approximation, not correct as per mathematical correctness, but it is analogy wise, it is a very correct explanation. Okay, then the incoming alpha particle could get very close to the positive charge without penetrating it, and such a close encounter would result in a large deflection. So the large deflection, the atoms, alpha particles which are coming back almost directly 180 degree, that is happening because when the alpha particle is going very close to that center, okay, it is coming back, but because it's very small, the number is very less. Okay, this agreement supported the hypothesis of the nuclear atom. So atom is basically concentrating one nucleus, okay, and the electrons are somewhere around it. Okay, how it is, we will see that in a while. This is why Rutherford is credited with the discovery of nucleus. So there was 1 year question, previous years they have asked who was given the credit for discovering nucleus. Okay, I have not included that question because it is a very simple question. So but you should know that the credit of discovering nucleus was given to Ernest Rutherford. Okay, Ernest Rutherford is the discoverer of nucleus. That credit goes to Rutherford. Okay, now the magnitude of this force is given by, the magnitude is somewhat important, sometimes they might ask you. So the magnitude of the repulsive force between the incoming alpha particle and the nucleus is given by this formula. Okay, Z is the atomic number. We will discuss about Z and everything in our next chapter. So far you just remember this formula. We will discuss this in our next chapter so that you don't get lost. Okay, now let us look into the another part, alpha particle trajectory. So if you see, as we discussed that atoms are going towards the so alpha particles are going towards the atom, and some are most of them are going straight. So this is the most amount of alpha particles are going in this direction without any deflection. Some of the atoms are deflecting like this, and 1 in 8,000 they are coming back almost more than 90 degree angle. Okay, the trajectory traced by an alpha particle depends on the one important parameter, impact parameter. Okay, so one important parameter is impact parameter. Okay, what is impact parameter? Impact parameter B of the collision. Okay, the impact parameter is the perpendicular distance of the initial velocity vector of the alpha particle from the center of the nucleus. So suppose an alpha particle is going in this direction, and here is the nucleus. So if you transfer it here, okay, and whatever the distance is, this is the starting point, this is the starting point, this distance is called impact parameter. Okay, closer it is, okay, there is a high chance that it will reflect back. Okay, if impact parameter is very small, of the 10 to the power of -8, -9, then there is a chance that it will reflect back directly. If the impact parameter is high, say 1 millimeter, then it will go straight without much deviation. So if the impact parameter is very small, then there is a high chance it will interact with the nucleus. It will interact with the nucleus, and it will come back towards the alpha particle source. Right? So this is clear. This distance is basically called impact parameter. Impact parameter varies from position to position. If impact parameter is high, it will go undeviated. If impact parameter is low, then there is a high chance it will be getting deflected by large angle. Okay. Now, a given beam of alpha particle has a distribution of impact parameters, as I said, so that the beam is scattered in various directions with different probabilities. So based on the impact parameter value, the alpha particle will be scattered in different directions. Okay, it is seen that an alpha particle close to the nucleus, smaller impact parameter, suffers a large scattering. In case of head-on collisions, the impact parameter is minimum, and the alpha particle rebounds back. So for rebounding, okay, it is a impact parameter is minimum. So minimum means almost zero. So if impact parameter is 0, then it will definitely rebound. So if they ask you a question, in case of rebounds, what will be the impact parameter? It will be 0. For a large impact parameter, the alpha particle goes nearly undeviated and has a small deflection. Okay, so for a large impact parameter, which is common because nucleus itself is very small, for a large impact parameter the alpha particle goes undeviated. Okay. Now distance of closest approach, very important concept. Okay, many students struggle to answer questions if question comes from in your PU board as well as in your KCET exam as well. What is the distance of closest approach? First let us understand. Throughout the scattering process, in the alpha scattering process, obviously throughout the scattering process, the total mechanical energy of the system consisting of an alpha particle and a gold nucleus is conserved. Okay, so in the scattering process, total energy, okay, or the gold is at rest, okay, but it has a potential energy, right, electrical potential energy. Alpha particle starts moving, okay, it has a kinetic energy, and when it is interacting with the nucleus or the atom, it develops a potential energy as well, right. So this total energy of the system should remain constant. Initial energy is kinetic energy, say Ek, and its final energy is potential energy, electric potential energy, say Ep. Okay, when the alpha particle momentarily stops, okay, all its kinetic energy is converted into potential energy. So suppose there is a gold atom, there is an alpha particle, it is moving, okay, when it is going here, suddenly it stops and then it comes back. So at this point, when it is at rest, at this point its entire kinetic energy converts into potential energy, and the distance between the atom and the alpha particle is called the distance of closest approach, generally denoted by a symbol d. Okay, so the symbol d denotes the distance of closest approach. Okay, so from the equation we can see that what is kinetic energy? Kinetic energy is half mv square. What is electrical potential energy? Electrical potential energy is k q1 q2 by d, right. If you remember in our electrostatic chapter, we have learned that potential energy is k q1 q2 by d. There is a value of q1, obviously one of them is 2v, one of them is zd. I am not interested in all the values. What I am interested is that the distance of closest approach is inversely proportional to the square of the initial velocity. Okay, so the distance of closest approach is inversely proportional to the square of the velocity. So higher the velocity, distance of closest approach will be smaller. Okay, obviously it is expected, right. So if you throw a object with very high speed, it is supposed to go very close to that object rather than repelling back it before even it reaches there, right. So distance of closest approach is definitely depends on the velocity. It is inversely proportional to the square of the velocity. Now let's look into one problem also from your previous KCET question paper. In alpha particle scattering experiment, if v is the initial velocity of the particle, then the distance of closest approach is d. If the velocity is doubled, then the distance of the closest approach becomes so we know that distance of closest approach is inversely proportional to the square of the velocity. So what we can write, suppose for first case it is d, it is v. Okay, for the second case, say it is now d dash and the velocity is 2v, right. Now what we will do, we will divide d dash by d. So d dash by d equals to this v was denominator, so it will go up v square. It was in the denominator, in this case we are writing in terms of d, so it will stay in denominator whole square. Okay, so v square by 4v square. Okay, so v square cancels, so d dash equals to 1/4 of d. Okay, so clear. So as you increase the velocity, the impact parameter, the distance of closest approach will be reduced by squared of that difference, right, squared of that times. Okay, so if you next time if they say this velocity is tripled, then what will happen, it will be 1/9. Okay, if the velocity is halved, then it will be 4 times. Okay, whatever they are saying, you have to square it and then inverse it. Okay, if they say squared it, they said velocity is increased by twice, velocity is increased by thrice, then the distance of closest approach will become square of the value 1 by that. Okay, 1 by square of the value. Okay, if it is reduced, say it is halved, or if it is 1/3, then you square it, again same process, 1 by, so that means 1 by 1/3 whole square, it will be 9 times, right? So remember that. Now electron orbits. So Rutherford said that electrons, where do the electron goes? Electron was discovered first by J.J. Thomson. Okay, at this point of time, neutron, proton, they are not yet discovered. Okay, so first time we are experiencing that there is a positive core. Okay, positive core at the center, we are calling it as nucleus. What happened to the electrons? Okay, so let's look into that. The electrostatic force of attraction Fe between the revolving electrons and the nucleus provides the requisite centripetal force to keep them in the orbit. So basically what we are saying that electrons are actually orbiting the nucleus. So they are moving around the nucleus. They are not static, they are not embedded inside the palm, but they are moving around the positively charged nucleus. Okay, so they are moving around the positively charged nucleus, and because this is positive, because this is negative, there is a force of attraction. Okay, and if you remember the chapter gravity, where we have studied the motion of satellites. Okay, we said there is a force of gravity. That force is actually providing the required centripetal force. Okay, so whenever there is a circular motion, remember that whenever there is a circular motion, someone has to provide the centripetal force. Centripetal force is not like something like repulsive force. Okay, repulsive force will be there as long as there is a positive and there is a negative, there will be repulsive force. Okay, so centripetal force has to be provided by someone. Okay, so that is why the concept of centrifugal force, which is pseudo force, becomes popular, because it helps us to balance the forces. But actually centrifugal force does not act on the object. Centripetal force is the real force, and centripetal force has to be provided by something. If our source of the force, whichever is providing the centripetal force, is not there, then there will be no circular motion. You have to be clear about that. Okay, so who is providing the centripetal force? Here the electrostatic force. So suppose the charge of the nucleus is E, okay, and charge of the electron is also E, then we can write the centripetal force as 1 by 4 pi epsilon naught E square by R square is equal to mv square by R. Okay, and from here you can even simplify the value of R to be E square by V square. So basically the radius of Rutherford model, R is basically proportional to the V square. Okay, so V square, it is proportional to the velocity of the orbiting electron. Okay, so whatever the velocity the orbiting electron has, okay, the radius of the electron is 1 by V square. Okay, proportional to 1 by V square. Now this is not 100% correct. We will discuss that in our board's model part, second part. Okay, but for now you can even find the kinetic energy. Okay, kinetic energy is E square by 8 pi epsilon naught R. Okay, this is just a value. In some case they ask you some question based on this. Rutherford model, Bohr model is more popular in terms of energy, radius, etc. But in case they ask some questions, some basic questions, so you should know this is also, how can you find the velocity, how can you find the radius in case of Rutherford model. So Rutherford said that atoms have a center core, highly positive, and electrons are orbiting around it. So that was the structure of atom. First semi-correct structure of atom, even though Rutherford's model was not correct. His student Niels Bohr corrected the actual model. So Niels Bohr, yes, Niels Bohr was a student of Rutherford, so he was doing his PhD under Rutherford, and then he took up the concept from his teacher, and he was in fresh mind, so he has made the correction which was required. We will do that in our next day lecture. Okay, and the energy, the kinetic energy is that, and potential energy is given by this. The negative sign represents that electron is bound to the nucleus. Okay, the electron is bound to the nucleus. The negative sign U signifies that the electrostatic force is in the minus R direction. So what is the plus R direction? If you remember, in electrostatics we always denote R in this direction, right? But the negative sign in U denotes that the electrostatic force is actually acting in this direction. Okay, or you can say that electron is bound to the nucleus. If you want to free that electron, you have to provide this extra energy so that the energy of the electron becomes 0 and it becomes free. Okay, if you remember the previous chapter, dual nature of radiation matter, photoelectric effect, how the electron is coming out, because electron is absorbing the energy, whichever energy is required to free it, and once it is getting that energy, it is becoming free, right? So this is all now making sense. The total energy E of the electron in a hydrogen atom is given by, and everything whatever we are doing, this is for hydrogen atom only. Okay, we will see that for any other atom other than hydrogen atom, even Bohr's model is also not valid. Okay, Rutherford model is not valid in any way. Okay, but Rutherford model is still okay. The total energy of the electron is negative. This implies that the fact that the electron is bound to the nucleus. Electron is bound to the nucleus. To move out of the nucleus, it has to gain some energy. Photoelectric effect, the radiation is providing that energy. Once the electron is absorbing that energy, it is coming out of the nucleus. Okay, now atomic spectra, one more important concept. Atomic spectra, we have discussed the characteristic spectra in our first part. Okay, that was the main starting point, that why palm pudding model was not correct. Scientists speculated that the palm pudding model should not be correct because each and every element has a specific spectra. Okay, and that spectra is helping us to identify. By seeing the spectra, we can identify what kind of material it is. Okay, if it is hydrogen, it is nitrogen, or any other gases or any other solids. And particularly this is very important when you are observing distant stars, distant solar systems. Okay, so for example, water has a particular characteristic spectra, and you are observing some planet, very distant planet, where future we will be making some spaceship like Star Wars, and we will be going there in future. So we have to know that, okay, there is a water or not. So how can we know that there is water? So if we observe their characteristic spectra of that planet, and if you see, okay, it has that characteristic spectra, that means in one form or other there is water present there. Okay, maybe it is present in terms of vapor, maybe it is present there as a ice, but there is water. So if we go there, if it is in habitable zone, we can survive. Habitable zone, there is a different theory altogether. So I am not going to display in this lecture, but you should know that based on these assumptions, they try to understand if there is any intelligent life available in that planet or not. So they try to send signal if there is water, but we know that water is most essential thing to survive, right? So we need water to survive. So similarly, all other organic animals must need water to survive. So that's how they do the observation in future. Even if we have to shift to the one of the moons of Jupiter, there is a very theory of that we are going to shift to the one of the moons of Jupiter, if it is habitable or not. So for that we have to know if there is water or not. Okay, one more, Mars. Nowadays very common thing is that Mars is whether we can shift to Mars or not. We cannot shift because there is not enough water. So if we want to shift to the water, we have to terraform Mars such a way that there is enough water, right? So this is one of the important thing, atomic spectra. By analyzing this, we can understand if there are some distant galaxy, distant planets, distant stars, they have some materials which may be present in our galaxy, present in our solar system, or not present in our solar system, both way. Okay, what is this? Each element has a characteristic spectrum of radiation which it emits. Okay, when an atomic gas or vapor is excited at low pressure, usually by passing an electric current through it, the emitted radiation has a spectrum which contains certain specific wavelengths only. So when you observe a particular element's atomic spectra, you will see some lines, some spikes. Okay, they all have some names. Okay, based on that lines you can say, okay, this characteristic, this is the characteristic spectrum of hydrogen, this is of lithium, this is of different element, right? So based on that spectrum you can identify. Let us look into one of the most common atomic spectrum, okay, of hydrogen, that is given by like this. So if you see a pattern like this, if you see the pattern like this, and they have some wavelengths also, wavelength does not matter, but if you see this pattern, okay, so there is 1 2 3 4 5 6 lines, then one line separated. So there are some lines close by, then some lines are spread out. So if you see this pattern, you will understand, okay, this pattern is only possible for hydrogen, so there must be hydrogen present in that distant planet, in that distant galaxy. Okay, so this is how we can determine. This is our in-house lab data. Okay, this was done in our Earth. Okay, not in-house here, but it is done in Earth. Okay, so we observed this. We have done all the available metals, all the available elements in our Earth, and we have recorded their characteristic spectrum. Now when we are analyzing data from a distant galaxy, if we see there is a match, that means that galaxy or that planet has this kind of material present in their galaxy as well. Okay, and this has some names. Okay, Lyman series, Balmer series, and Paschen series. Okay, Paschen, some say Paschen, some say Paschen. Okay, I say Paschen. So Paschen series, Balmer series, Lyman series, these are the three series. Okay, in out of that, Balmer series is in visible zone. Okay, if you heard the name hydrogen lamp, okay, hydrogen lamp is basically when you excite the hydrogen gas in a tube in Balmer series zone, then it emits a particular color of light, and that is called Balmer series. Okay, Balmer series is in the visible zone. You should know that, even though these series used to be very important, because there was a formula based on that you have to calculate the different wavelengths, etc. But now that part is deleted. Only leftover thing is this graph, this expression. Okay, this what I say, this figure. Okay, only this figure is there. Other than that, all the mathematical portion is deleted, so you can enjoy. Okay, don't worry, don't take too much stress. Okay, only the names you have to remember. Also one more information, that Balmer series falls in the visible zone. Okay, as you can see, 365 to 756 nanometer. So this is around red light. This is slightly more than violet light. Violet light comes around 400. Okay, and red light ends at 700. So this series is within our visible zone. We can see most of the lines. Some of the lines are outside, obviously. Some higher wavelength lights are not there. Okay, so higher frequency lights are not there. But this Lyman series and Paschen series, not a single line is present in our visible zone, so we cannot see this. Okay, to observe this series, we have to take use of photographic plates and then analyze it. Okay, so there are different ways to do that, but this Balmer series we can observe in our naked eye. Now let us look into the homework question for today. So you can pause the video, you can answer the question and mention the answer in the comment below. Second homework question, I will be solving them in our upcoming video, atoms part 2. So don't worry if you are not able to solve them. You try to read these questions. I have given enough hints while doing the lecture, so you should be able to answer these questions. Read the question and mention the answer in the comment below. Now if you are wondering where you can get all the videos, it is a very long series, as we are doing one video every day. Don't worry, we have a dedicated playlist where all the videos related to physics KCET 2025 are there. You can visit this playlist, you can bookmark it, and you can study at your own time, at your own pace. So don't worry, all the videos, whatever we are doing, even if you're missing today's video, you can watch it maybe 1 month after, maybe day after tomorrow. But I will suggest don't wait too long, because it will create a long-term gap, it will create a long-term backlog. So don't fall behind too much, but you can study from this playlist at your own time, at your own pace. Okay, and moreover, you have to join our WhatsApp group so that you don't miss out on any important notification. And if you think this is helping you, don't forget to leave it a like, and you should subscribe to our channel, share it with your friends. I'll be back with atoms part 2 tomorrow. Thank you for watching.